So as you have seen for the triple point, solid vapor, liquid vapor, basically solid liquid vapor coexistence, right? We have derived, right, that T3, which is the triple point temperature, is related to the difference in the heats of transformation of alpha to gamma. Alpha to gamma is solid to gas, and liquid to gas transformation, right? Beta to gamma is liquid to gas, and it has also this relation to this AS and AV, right? These are the coefficients, right? AS and AV. Now this is T3. Again, some algebraic manipulation later, we have shown that P3, that is the triple point pressure, again is related to these coefficients AS and AV. And remember the coefficients. This is something that you have to remember. How did we look at the coefficients? We did this thing, right? P equal to P naught e to the power minus chi. So P naught basically, for example, e to the power minus chi. So here P naught is the coefficient, right? Here P naught is the coefficient. So we can basically, the coefficients are related to the P vapor or P sublimation, means the temperature at which sublimation occurs, or the pressure at which sublimation occurs, the temperature at which sublimation occurs. So these are basically, the pressures are going to be the coefficients. So if you look at that, AV, if you see the relation, this is pressure, right? This is pressure. So this is in Pascal. So then the exponent has no unit, right? The exponent has no unit, right? It's joule by joule. So it has no unit. So obviously AS. So basically AS comma AV, these are basically going to be units of pressure. So these are units of pressure. And if you compare, these are nothing but AS and AV are nothing but some standard pressures of transformation from either from solid to gas, right? Here it is solid to gas transformation, or say liquid to gas transformation. And AS, for example, is basically a standard pressure of, so it can be like standard pressure of sublimation, right? This can be standard. So in this case, this is beta to gamma. So this is like standard pressure of vaporization, and then there is some. So we can think of some standard or reference state, and that this is again at that reference state P naught S. So basically P naught S, or so basically AS and AV are related to, we can tell, are related to P naught S or P naught V, right? P naught S basically, or P naught sublimation, and this is P naught vaporization, right? So these are related. AS and AV are related, right? AS is related to P naught sublimation and AV is related to P naught vaporization. Now see, you have this, then think of this, you have this relation. Again, you see here, this is AS and this is AV, both have the units of pressure. So again, within Ln there is no unit. So you have here joules per mole Kelvin, and you have here also you have, so R is joules per mole, this is joules per mole, and this is joules per mole Kelvin. So you can see this gives you Kelvin, right? It gives you Kelvin. So temperature, the unit is in Kelvin, and you see these are related to the difference in heats of transformation of alpha to gamma. Alpha to gamma, remember, this is like solid, this is solid to vapor, this is liquid to vapor, solid to vapor, and this is liquid to vapor. Now as you know, solid to vapor is like solid to liquid, liquid to vapor. You can think of that. Okay, now if you do a little bit of algebra, okay, again taking ln on both sides, basically you are taking ln on both sides. Okay, you have taken this expression of T3, you put that here. Okay, you have taken this expression of T3, you put T3 expression here, right? Right. So, or say in the previous expression here. Okay, so here you are taking the expression for T3, right, at R3. So if you do that, and then you take ln on both sides, logarithm on both sides, and you can basically come up with, so delta HD, for example, here I have told is basically the difference between this, right? Alpha to gamma transformation enthalpy minus beta to gamma transformation enthalpy, right? So now you can basically, with a little bit of rearrangement and algebraic manipulation, you can come up with this expression. Okay. By the way, in the exam, if I give a question related to this, I will basically give these expressions. Okay, you don't have to remember anything, but you have to understand. Okay, what you have to understand is that P3 is related to this, again, the pressure. There is a pressure and there is an exponent, and this exponent is, again, you see AS is related to beta to gamma by beta to gamma minus alpha to gamma. Right? This is basically the exponent is a ratio of enthalpy of beta to gamma by the beta to gamma minus alpha to gamma, the enthalpy difference. This is the transformation, the enthalpy of difference in the enthalpy of transformation, and this is the enthalpy of transformation from liquid to vapor. In this case, this is from solid to vapor, and again, this is the difference between the enthalpies of transformation of solid to vapor, difference between solid to vapor and liquid to vapor, right? And again, AV is one pressure term. Now, if you have this, you please try to understand that this is an exponent here, right? This is a power here. So, as you know that this logarithm and exponents becomes gives you a very nice way to deal with the triple point calculation. So basically what it tells you is that if you do ln P3, then this guy comes down or this guy comes down, right? So if you do ln P3, you can write it as a very simple expression in terms of this coefficient times ln AS plus this coefficient times ln P. So basically logarithm, so P, if I can use a logarithmic scale, calculations become easier. Further, you can make some approximation that the triple point in general at 1 atmosphere pressure or at not 1 atmosphere pressure, at pressures below 1 atmosphere, the triple points are very close to the melting point. So how do you do that is coming this example, right? I started with this example, so I will go farther down. So we have, this is basically phase diagram of silicon. It's a very important material now. It's a semiconductor, so it's a phase diagram of silicon. You have to process silicon, you have to make silicon as pure as possible. Now again, look at silicon, and if you look at silicon, silicon can sublimate. Say basically the sublimation, the enthalpy of sublimation from alpha to gamma for silicon again can be written as sum of enthalpy of melting of silicon plus, right, alpha to beta is melting, right, liquid to solid, and enthalpy of beta to gamma, right, delta H alpha to gamma. So alpha to gamma process is subdivided into two processes, alpha to beta and beta to gamma. Now see another thing, as I told in the previous lecture, that boiling point has to be greater than the melting point, right? The boiling point usually is greater than the melting point at 1 atmosphere pressure. See 10 to the power 0. So excuse me. So so as you can see, this is pressure in the log scale. Okay, we have plotted pressure in the log scale, and the pressure's unit is in atmosphere. So this is 10 to the power 0. So 10 to the power 0 means 1 atmosphere. So this is basically 1 atmosphere pressure, and these pressures are much below, right? You can see here it is 10 to the power minus 25, right? It's 10 to the power minus 25, which is like a very, very low pressure, and then this is like 10 to the power minus 5. How did I get into this point? So basically, if you now look at it, you have pressure plotted in the log scale, and you have temperature. On the above axis I am plotting temperature, and you can at 1 atmosphere. So you can see I have plotted here 2 points. I know the melting point, and say I know the boiling point at 1 atmosphere for pure silicon, right? This is pure silicon, right? I know the at pure silicon, this is room temperature. So this is 1 atmosphere, and this point corresponds to room temperature. These points corresponds to melting point, and this is the boiling point. So I have plotted these 3 points only. Okay. Now you see at 1 atmosphere and 300 Kelvin, this part is definitely going to be solid, right? And then beyond melting point, this is liquid, right? And then beyond, so this part is liquid, right? This is solid, this is liquid, and this part is basically the vapor, the silicon vapor, right? So because it is above boiling point. Now this is all at 1 atmosphere, right? We know at 1 atmosphere. Now you see I have these 3 points. I also need to know the enthalpy. Say for example, this is the delta H of pure silicon from liquid to vapor, and we know, say that it has 386 kilojoules per mole. right? 386 kilojoules per mole measured at 1 atmosphere and at the boiling point, which is 2873 Kelvin, right? So we need to know the boiling point, right, at 1 atmosphere. So we know that. Now if I know that, then basically I can calculate AV, right, which is basically equal to PV times e to the power. Now this becomes, so PV was AV times e to the power minus delta HSI by RT. So AV will be PV times e to the power plus delta HSI by RT, right? This minus sign is not there. So minus sign has become plus, right? Because I have taken PV on this side. So I have taken the exponent on the PV side, on the pressure side, PV side, and this is the PV naught. And so basically PV, if I put in as 1 atmosphere, then I get 1.04 into 10 power 7 atmosphere as AV, right? So basically I get AV coefficient as 1.04 into 10 to the power 7 atmosphere if I plug in this value of 386 kilojoules per mole for liquid to vapor, and I plug in R and I plug in T equals to 2873, then I get this, right? Now I also know Tm, right? I also know Tm. Now I make an assumption. I tell that in such a setting, the T3 is not very much different than Tm, because T3 has to lie between melting and boiling point, right? So if T3 has to lie between melting and boiling point, we are assuming that, let us assume that Tm at 1 atmosphere, that 1685, that T3 at whatever be the pressure, I don't know the pressure yet, but I am assuming T3 to be 1685. Now I also know the enthalpy of transformation of silicon from solid to liquid, which is 50.2. Again, it is plus because solid has to absorb it and then it will transform to liquid. Now, if you have all this information, what information do you have? You have this information, you have this information, and you also know the coefficient AV, right? But you are also assuming T3. Now, if you are assuming T3, you can calculate P3. How? You have PV, which is basically 1.04 into 10 power 7, right? PV is equal to 1.04 into 10 power 7 into e to the power minus 386000 by 8.314 T. Now, at P3, T has to be equal to T3, right? T has to be equal to T3. So, as you can see here, first of all, I calculated AV. How did I calculate AV? I substituted PV equals to 1 atmosphere, and then I looked, right, because we are looking at 1 atmosphere boiling point, and then I plugged in the boiling point here and I got AV. Now I take the same expression here, so PV equals to AV exponential minus delta HSI. So PV equal to AV times, now if I take it this way, exponential minus delta HSI L to V by RT. But we are telling T3 is the same as Tm. Okay, this is an approximation. T3 is the same as Tm, and basically I plug in T3 here, right? If I plug in T3 here, so I get P3. So P3 is 1.13 in the minus 5 atmosphere. So basically at this point I mark this point. So I join them, right? I join them, and then I have also TB, so I join this and I go farther down. Now what is this pressure? Can anyone tell me? So this is the pressure. This is, see, this pressure corresponds to something like slightly above 10 to the minus 25, but that's 300 Kelvin. So what does it tell you? So you think about it, but I'll tell you. Now if you see, so I got P3. So basically I know, if I know T3, that it does not shift too much, then T3 does not shift too much from melting point, if I tell, right? Why can I tell that? Because T3 has to lie between Tm and Tb, and in all practical purposes, as I go towards low pressure, so it will shift more towards Tm, right? The T3, the triple point has to shift more towards Tm. So basically this point O signifies your, so this point O signifies your T3. So T3 and Tm are same, and we got P3 from this expression, right? From this expression. And we have calculated AV assuming P equal to 1 atmosphere and TB equals to 2873 Kelvin. But as you know that this equation holds true for P3, means for the temperature when T equal to T3 or the triple point temperature. So we know the pressure. Now you see, as I told you, that the enthalpy of transformation of pure silicon from solid to vapor is the sum of enthalpy of silicon from solid to liquid and enthalpy of pure silicon from liquid to vapor. That's the sum, right? A solid to vapor is solid to liquid, liquid to vapor. So you can see here 50.2 plus 386, which is 436.2 now kilojoules per mole. And basically now AS, so basically you can get now AS value, you have 1685, and what will be, this is P3. So basically from there you can get the heat of the pressure of sublimation, the pressure of sublimation at different temperatures. Now tell me, at temperature T equal to, say, if I take temperature T equals to say 300 Kelvin, then find out what will be PS. Okay, so that is one task that you have. You find out the pressure. Okay, now remember, PS is the pressure of vaporization. So here, when we are looking at here, what is the phase we are looking at? Is it the solid phase? Now solid phase here is going to gaseous phase. Are you seeing that? So basically the solid phase at this point, if you see, this is a critical point, which basically this is like a phase boundary point between solid phase and vapor phase. Now at 300 Kelvin, this is the pressure that will basically, this is the pressure of transformation, or at this, at 300 Kelvin and at this pressure, solid and gas will coexist, right? Solid silicon will coexist with gaseous silicon, right? Or vapor silicon, right? So find out this pressure. You see whether you get a pressure which is corresponding to this value. So you have T equal to 300 and you find out the pressure. Okay, so this is how you can check that you are more or less correct with the assumption that Tm in the log, because see, the variation in pressure is very, very minuscule, right? That's why I am using, so the variation means basically like 1 atmosphere, this is 10 to the minus 5 atmosphere where you are getting this thing, right? And you see the for solid to vapor, the pressure has to be very, very small, right? Pressure has to be very, very small for solid to vapor coexistence in silicon, right? So, and the pressure has to be reasonably high for solid to liquid coexistence to happen, right? And this is where solid, liquid and gas, right? Solid, liquid and gas can coexist. Okay, so that is the idea that I am trying to tell. Okay. So this is coming from, by the way, this is a book from, this is an book example. This is an example from Professor de Hoop's book. Okay, so this is Robert de Hoop book. If you look at Robert de Hoop books, de Hoop's book on thermodynamics in material science, you will basically get this example, okay, in chapter 7. You will get this example. It's a very nice example and a demonstration that Tm and T3 does not really change too much, okay. And as you can see, what we have done, we have taken a baseline of 1 atmosphere and we are looking at pressures that are lower, and as we know that the triple point always will shift to the triple point where solid, liquid and gas will coexist, will always shift to lower pressures, right? It will always shift to lower pressures. You can think of any other example, you can repeat this the same idea and you will basically see that the triple point always shifts. The triple point is where the solid, liquid, gas coexistence in most of the pure substances basically shifts towards lower pressures, right? Near the melting point, right? So now there is one very important example that I'll give. Okay, again, it comes from a problem that is given in an exercise in Professor de Hoop's book. Okay, so this problem is basically, so as I told you, so this is again the way I have drawn this. These are all, assume that these are all basically, this is not like I am taking it from a CalFAT database or something. This is an approximate analysis, but although it's an approximate analysis, it gives you a very good approximation of the actual values. Okay, I am not taking the CalFET, I am not taking the database that is basically coming from the experimental data and fitting it to some curves. I'll come to how this CalFET procedure is done. I'll give a brief about how this is done, but please try to understand these are basically approximate free energy curves. So these are basically the molar free energy curves as a function of temperature for 3 phases. Okay, in pure titanium. So this is the epsilon phase or the FCP phase. As you can see, as you go towards, as you are in the lower temperature regime, so basically less than TA or T epsilon beta. Okay, A is nothing but T epsilon beta. As you are less than T epsilon beta, you see epsilon to be the lowest energy phase, right? Epsilon, so basically below A, epsilon is the lowest energy phase, right? This is mu versus T. Remember, this is not a phase diagram, right? This is basically giving you 3 free energies. One is for liquid, one corresponds to beta, one corresponds to epsilon, right? This is the epsilon free energy as a function of temperature. Let us assume the pressure is kept constant at 1 atmosphere or 1 bar. Okay, pressure is kept constant at 1 bar. We are looking at the variation in free energy as a function of temperature, and this is pure titanium. And as you can see, below TA, epsilon, right? Epsilon has the lowest energy below TA. Then between A and B, that is below TB, which is the epsilon. So B is basically a very special point. So I'll come to that. But as you can see, between A and C, look at the green curve here. Look at this. This is the green curve corresponds to the energy of the BCC phase beta. Okay, BCC allotrope of titanium or BCC structure of titanium. Okay, or this BCC phase of pure titanium, which is beta. Right now, as you can see here, in this regime between A and C, this has the lowest energy, right? This has the lowest energy from the diagram. So basically here, if epsilon is stable, here beta is stable, and here, as you can see, this blue corresponds to the liquid phase. The blue curve corresponds to liquid phase, which has higher energy up to C, but beyond C, titanium has become liquid, right? It has become liquid. So now I will talk about metastability. Metastability is when does it happen? Metastability means basically a phase that has higher energy somehow appears because the lowest energy phase somehow does not form. For example, diamond has formed instead of graphite, although graphite is the lowest energy phase of carbon. Somehow, due to certain conditions, you see that graphite is absent and you have formed diamond, and diamond to graphite transformation does not take place at all. So it remains as it is unless you give a very large energy, or there is a very large energy input. Diamond will remain as diamond. It does not convert to graphite. Okay, so you will soon see that in steels, for example, there is some phase called cementite. Okay, which is an integral part of perlite, right? Of perlitic steels in cementite. The lowest form of the lowest energy phase, okay, at room temperature is not cementite, but it's graphite. But once cementite is formed, it does not transform to graphite or diamond. Okay, so that is the point. So think of this. You have now, if you look at this, if you do not think of metastability, everywhere you have epsilon. Epsilon is the lowest energy phase below TA. Beta is the lowest energy phase between TA and TC, and beyond TC or T beta liquid, this is the liquid is the lowest energy phase, right? The blue phase is the lowest. The blue free energy curve is lowest. Then green free energy curve is the lowest in the A to C regime, and here this orange one is orange one is here. So if you look at that, orange one is here and the green one is here, and this is where it is the liquid, right? The blue one, right? So basically you can see that this coexistence happens if you have no metastability. Now think of this. So I'll just try to select this. And I'll paste it. Now as you can see here, I will erase this curve. Now if I erase this curve, there is no beta. There is no beta. And you have now only one temperature here, because now beta phase does not exist. Beta phase, which was a stable phase at the intermediate temperature between A and C, does not exist. If that does not exist, then these lines are also not there. Now you have epsilon L coexistence. You have epsilon L coexistence, right? So epsilon is the low temperature phase, okay, and liquid is the high temperature phase. So epsilon converts to liquid. So we are telling now find T epsilon L. So what we told, I know 2T epsilon beta, which is the equilibrium transformation. So I know T epsilon beta, right, which is basically A point. I know T beta L, which is again an equilibrium point. I want to find T epsilon L, which is basically, see, the T epsilon L should not have appeared. If there would have been beta, then T epsilon L does not exist, because this is that much higher, the energy is much higher than the green phase, right? The green curve. The green curve corresponds to beta phase. So beta phase will obviously appear below this, right? So basically beta phase is more favorable here. However, because of some reason beta phase is not formed. So what is this temperature? And that's what I am telling here. Okay, so this is basically where the beta phase, which is the most stable phase at the temperatures between A and C, right? At temperatures between A and C, beta phase is the most stable phase, but it is somehow absent. It did not form. So now you have a metastability between epsilon and L, right? A metastable equilibrium between epsilon and L, right? Now you want to find out this. Okay, now see, think of this. We know, now you want to find out this, right? Melting point of epsilon Ti. You want to find out melting point of epsilon Ti. Again, when you do any such problem, as you have seen before, whenever I have given examples, what I have done, I have gone to the final expression, then I have put values. I don't put values from the beginning, okay, because then sometimes you may make mistake in getting the correct expression. So first of all, if you think of melting point of epsilon Ti, you have to think of this equilibrium, right? The free energy of epsilon, this is the metastable equilibrium, that the free energy of epsilon equal to free energy of liquid. That's a metastable equilibrium. Now think of this, if mu epsilon equal to mu liquid, I can take mu beta out on both sides. So now you have mu epsilon minus mu beta equal to mu L minus mu beta. Now if you think of this, the way we have written, that means this is delta mu beta to epsilon, and this is delta mu beta, to epsilon, which is basically minus of delta mu epsilon to beta, right, which is minus of delta mu epsilon to beta. Okay, and this is happening at what temperature? So this is happening at T epsilon L. So that means this equation is also valid at T epsilon L, right? And we want to know what is T epsilon L. So now think of this. You also know, for example, the delta Sm, that's the entropy change. So obviously the entropy, so the more stable phase, that higher temperatures, the more stable phase will have more entropy. So if you think of that, then delta Sm epsilon to beta, which is Sm beta minus Sm epsilon, which is equal to plus 3.6, right? Sm beta minus Sm epsilon at 1155 Kelvin. So Ta equals to, so basically T epsilon to beta is equal to, or T epsilon beta in short, is equal to 1155 K. And for epsilon to beta transformation at T epsilon beta temperature, the entropy change is plus 3.6 joules per mole Kelvin. Remember, it's plus 3.6 moles per joules per mole Kelvin. And as you know that at T epsilon L, okay, as you know from this curve, that at T epsilon L, the free energy at T epsilon L, mu epsilon is greater than mu beta, right? The free energy of epsilon is greater than free energy of beta at T epsilon L. So now think of this, you are doing an integration, okay? You are doing an integration, okay? And also remember, we are doing it at constant pressure, and you know mu equals to minus S, small s, okay? This is entropy per mole, dt plus V dP, and it's constant pressure, so it is minus S dt, because dP goes to 0. So you have minus Sm dt, okay? So similarly, you can write d mu beta to epsilon is minus delta Sm beta to epsilon. Remember, it is minus delta Sm. Why? It is minus S dt, and you see, you are going from beta to epsilon, right? Minus delta Sm beta to epsilon, okay? And what is the temperature? You started with TL, right? You were here, you were in the T epsilon liquid, right? That was your temperature, right? This is the equation we have written at T epsilon liquid, right? This is T epsilon liquid or TB. So this equation is valid at TB, right? So if you see, we are starting with T epsilon L and we are going to T epsilon beta. Now you please note that this is beta to epsilon. So basically you are looking at beta to epsilon transformation. Now beta to epsilon transformation. So this is basically epsilon to beta transformation, which is plus. So beta to epsilon will be negative, right? Okay. So basically, so delta minus delta Sm beta to epsilon is nothing but delta Sm epsilon to beta. And this is nothing but T epsilon beta, right? This is T epsilon beta minus T epsilon liquid. So this is your first equation. So this is your first equation. Mu epsilon minus mu beta is basically delta Sm epsilon to beta, T epsilon beta minus T epsilon liquid. Now remember, T epsilon beta is lower, right? According to our curve, T epsilon beta is at a lower temperature than this is higher temperature, right? And this is delta Sm epsilon to beta, okay? Now you see, mu epsilon is greater than mu beta is what we have. We know, right? But now this mu epsilon is greater than mu beta at T epsilon liquid. Now, but at T epsilon beta, just below T epsilon beta, for example, mu epsilon is less than mu beta, right? So these are the things that you have to understand. And if you see, I just use this equation mu equals to minus S dt to get this equation, right? And I have taken T epsilon L as the reference, right? This is the temperature that I want to find out, right? But T epsilon beta, the equilibrium temperature is known, and we know delta Sm beta to epsilon, okay, beta to epsilon at so I know, say for example, delta Sm beta to epsilon. Now I have made an approximation here. I am telling that I know the delta Sm beta to epsilon or epsilon to beta at the transmission temperature T epsilon beta, but I do not know at T epsilon liquid, but I am assuming it to be the same. That's why I have taken it out of the integration. Otherwise, I should have known this variation, and I should have. So this is an approximation that we are using, right? This is an approximation, because delta Sm can be a function of temperature, and it will change from one equilibrium temperature to another. So this is the metastable equilibrium temperature. This is the epsilon beta equilibrium temperature. At this temperature only I know this, but we are assuming that this is the same here also. Okay, so now we are telling this equation. So that's how we arrive at this equation. Similarly, for beta to liquid, you have minus delta Sm beta to liquid. Now beta to liquid is all our equilibrium. Only thing that you have to remember, that you have T epsilon L as the reference temperature. That is the starting temperature. So minus delta Sm beta to liquid, again minus delta Sm beta to liquid, T beta liquid minus T epsilon liquid. Here remember, T beta liquid is greater than T epsilon liquid. This is less than T epsilon liquid, right? Now you see, mu L minus mu beta is this, right? Now this is your equation number 2. Okay, so equation number 2. Now if you see, this I have labeled as equi. So equi tells you this equal to this, mu epsilon minus mu beta equal to mu L minus mu beta at T epsilon, right? Liquid. So we are telling that from equi 1 and 2 are equal, right? 1 and 2 are equal, because all of these we are looking at the changes, but we are looking at the changes from the same reference state, which is the T epsilon liquid, which we do not know. Now if I do that, if I equate that, then I basically get this relation, delta Sm epsilon to beta, T epsilon beta minus T epsilon liquid equal to minus delta Sm beta to liquid, T epsilon beta liquid minus T epsilon liquid. Now if I arrange a little bit, I get this. See, delta Sm epsilon to beta. So basically this one, this guy and this guy, and this guy and this guy, I am taking to the same side. So this times this and this times this, and see there is a minus sign. So if I take it here, then it becomes plus, and this is this. So basically now you want to find out T epsilon liquid, and as you can see, T epsilon liquid terms I am taking to the, so this term I am taking to this side. So if I do that, the minus sign, so it's plus sign, and this also has a minus sign, so this becomes plus. So this becomes just a summation of this times T epsilon liquid, delta Sm epsilon to beta, beta to liquid. See, if you see, there is a very interesting connotation here. See, epsilon to beta, beta to liquid, the sum is there. So this is basically delta Sm epsilon to liquid at T epsilon liquid, right? So basically I want to find out, but I still do not know T epsilon liquid. Again, these we know at the transformation temperatures. Remember, we know this as T beta L, this we know at T epsilon beta, right? These, but we are assuming that the values do not change. The values do not change at T epsilon liquid. Okay, if we use this approximation, since I know these values, now see I am plugging in the values. If I plug in the values, then basically I get, and this is delta epsilon to beta, is 3 plus 3.6, beta to liquid plus 8.6. So what we get is T epsilon liquid equal to 1710 Kelvin. Right? We get 1710 Kelvin. Think of this now. It's very, very interesting. This is 1155 Kelvin, which is epsilon beta coexistence. And what is the beta liquid coexistence temperature? Beta liquid coexistence temperature is 1943 Kelvin. So if you see this, if you see the curve, this is 1155 Kelvin. How much is not 1155? Yeah, 1155 Kelvin. And this is 1943, and this we found out to be 1710. Basically, if you do with any CalFAT, later I will show you that even with CalFAT databases, you will get very close to this temperature when you are looking at this metastable epsilon to liquid transformation. Okay, remember, metastable epsilon to liquid transformation only can happen if beta phase somehow does not form in the system. Beta phase is not forming, although beta phase has lower energy, right? So metastability is always greater than, means in terms of energy, metastability is having a metastable equilibrium has a higher energy corresponding to the stable equilibrium. Stable equilibrium is the lowest energy state. So if I say the stable equilibrium does not happen, then what you now look at is there any metastable equilibrium in the system? Okay, so this is how we do the analysis. So this is one example I gave you. I think that this makes sense to you, and if it does not, you please let me know where you are not understanding in the comment section. Then I will definitely try to answer as quickly as possible. So this you don't have to care about. So I have already done this, so you don't require to look at this. Means this is one more approach by which you can get it, but I don't think that is required. Again and again, what I am trying to say, only thing that, see, I have come up with an expression. Where I haven't used any values. At the end only, from in this expression that I have derived, I plug in the values and I get the metastable transformation temperature. Okay, so this is something that you should follow. Now I come to a very interesting topic called thermodynamics of solutions or mixtures. You can call it thermodynamics of mixtures. Okay, mixture means you are now looking at a multi-component system. However, I will in this particular case, I will think of a multi-component. So there can be solution, say for example salt dissolving in water. So you have two components, salt and water, and it forms a solution or a mixture, right? Or sugar water mixture, or say for example copper nickel mixture, like copper nickel alloy. It's a mixture of copper and nickel. okay, which forms a solution. Okay, a solid solution. You can have a liquid solution where two liquids are mixing, for example, water and alcohol, or water and oil. Okay, at some high temperatures they mix. So two liquids mixing is one case. A solid dissolving in a liquid is another case, or two solids mixing is also another case. Okay, these are all like, one is a solid solution, one is a liquid solution, one is some sort of a, ultimately sodium chloride is mixing with a solid mixing in a dissolving in a liquid, right, forming a solution. So we are looking at all of this. However, we are looking at non-reacting. Okay, so we are not currently we will not consider reaction, but soon I will consider it. But this is a non-reacting system. Currently we are considering multi-component non-reacting system. The first thing that comes in is, I will define now formally that, I have already defined something called a partial molar quantity, but I will tell you what does it. So for example, I have introduced chemical potential, right, for a multi-component system. I have already done it. So these quantities like chemical potential are called partial molar quantities, or partial molar. Some books like de Hoff's book calls it molal. Okay, so partial molar or partial molal quantities. Okay, so partial molar, in de Hoff's book it's called, instead of molar, de Hoff writes it as molal quantity, partial molal quantity. Okay, now, so think of this. You have a liter of pure water and is mixed with 1 mole of water. 1 mole of water at 25 degrees Celsius, 1 bar pressure. Now, raw water is 1 gram per centimeter cube, that we know, and 1 mole of water contains 18 grams of water. So 18 grams and divided by density gives me 18 centimeter cubed, which is like 18 to the power minus 3 liter, or 18 milliliters. 18 milliliters is the same as 18 cc. So basically the delta, so new volume is, the new total volume is 1018 ml, because it was 1000 ml to begin with. Now you have mixed water with water, so it has gone to 1018, and you get delta V, which is 18 ml. Now you will see an interesting problem. Now if you have, so you have this molar volume of water, which is 18 centimeter cube per mole, right? We have mixed one mole of water, and you are basically, you mix 1 mole of water, you raise the volume by 18 milliliters, so that, or 18 centimeter cube. So that means the molar volume of water has to be 18 centimeter cube per mole, right? Now think of this. You have 1 mole of water, but you have 1 liter of pure ethanol, right? And there is an increase in volume, but this delta V mix now is 14 centimeter cubed, or 14 ml. Why? See, it has to be, you have the same 1 mole of water, so it should have raised by 18 milliliter or 18 centimeter cube, but it has raised only by 14 ml. This is because of the association of water molecules with the ethanol molecules. What will you see if you look at the microstructure? If you look under a microscope, you will see, means a powerful microscope, you will see that each water molecule is surrounded by ethanol molecules. Again, each ethanol molecule is surrounded by water molecules. So there is some pack, means the packing happens in this fashion, right? You have water molecule, you have say a water molecule, and then there is this ethanol molecules, and then again you have one water molecule, each water molecule is surrounded by several ethanol molecules, and each ethanol molecule is separate. So basically, ethanol, if you go to a water molecule, you will see it surrounded by ethanol, and if you go to a ethanol molecule, you'll see it surrounded by water. So in some way, this association has taken place, and that results in a delta V mix, which is less. The association that has happened has reduced the increase in volume. It is no longer 18 milliliter, it is now 14 milliliter. Okay, because of this association, something has happened, some packing, some interaction, something has happened in such a way that the delta V mix has come out to be 14 milliliter per mole. So now think of this. Now think of partial molar volume. What is the definition? Of components of a mixture vary with composition as the environment of each type of component changes with the change in composition from pure A to pure B. So pure A, for example, is say pure ethanol, and pure B is like pure water. Now as you change from pure A to pure B, pure ethanol to pure water, that means I am adding some little bit of water to pure ethanol. Every time my association is changing, association between A and B is changing, right? Because A is surrounded by B, surrounded by A, like that. So as a result, the volume, the amount of volume that will, the volume, that overall volume change in the solution can basically be less than that were with pure water or with pure ethanol. Like you have pure ethanol, you add some little bit of 1 mole of ethanol, you will get a molar volume of ethanol. Now, if you add water to 1 liter of water, you will get the 1 mole of water, you get molar volume of water, right? You get molar volume of water when you, the exact molar volume of water, when you add 1 mole of water to 1 liter of water and find the change in volume. That change in volume is the molar volume of water. Similarly, for pure ethanol, if you add 1 mole of ethanol and you find the change in volume of the mixture, then you can tell that is the molar volume of ethanol. However, when it changes from A to B, that is from pure ethanol to pure water, right, you are adding more and more water, so that you go to such an extreme dilution that ultimately it's all pure water, there is no ethanol left. But you think of this as you change from pure A to pure B, what is happening is because of the association between A and B and because of the interactions between A and B, what you will see is the volume change, the delta V is not that of, which does not correspond to the molar volume of ethanol or molar volume of water. It is something different because of the way association has happened. Okay, we will look at how this association happens, what are the different interactions that can happen, like AA interactions can happen, BB interactions can happen, AB interactions can happen, which interactions are stronger, which interactions are more favorable. All these things basically lead to this change. Okay, and that change, that the amount of the contribution of water to the volume change of the mixture of ethanol and water is what is called as partial molar volume. So if you think of this, see, this is the partial molar volume of water. So this is again from Atkins' book. I have adapted this drawing. So if you look at that, this is partial molar volume of water, this is partial molar volume of ethanol, pure ethanol in centimeter cube per mole. As you can see, this is basically, if you think this is basically changing. Now this is 0 to 1.0. So here you are looking at, like, say for example, you think about it. Okay, so you think about it, which is, so if you are looking at this, you are having 14. So if you drop here, so as you can see, the partial molar volume of ethanol. So partial molar volume of ethanol here is low. On this side is low. On this side it is very, very high, right? On this side it has increased. So is it, so, and again for water it is here quite high, which is 18. Are you seeing that? 18 centimeter cube per mole. So that means this is the pure water, right? So it was 18, like pure water, which is basically zero ethanol, and this is pure ethanol, which has 58. So this 58 number and 18 number are basically the molar volume of water itself, VH2O, Vm, basically you can call it like Vm H2O when you have pure water, and this is Vm ethanol. But as you can see, it is changing, right? It is changing from, it has, when you go towards pure water, it has not abruptly gone to, 0 or anything, right? But it has some value here. Actually, this is an approximation here. In general, if you look at it, you will say that it has gone to a very, very low. So basically, if you see, it's a pure alcohol, it's like pure alcohol, then it's not So 0 to 1 is not is some sort of an exaggeration, but you can see that at pure ethanol end, the molar volume of water has changed to 14. It has changed to 14. See this. Pretty near pure ethanol, it has changed to 14. So you remember, please note that the partial molar volume does not exist. Basically, it is like if you see that it is going towards 1 and it is going towards 0. So it's not like, it's like 99.99%. It means it's like it's not full 1 pure ethanol. If you think that way, also is fine, but it is like pure ethanol as a molar volume, as you can see, as 58. So now I am telling in that approximation means the concentration of the solvent tends to pure ethanol. At that concentration where you add some water, 1 mole of water, which is very little amount of water in a very large volume of ethanol, then the molar volume contribution is coming out to be 14. Right, and then it rapidly increases. As it increases, so as you can see, this is the molar volume of ethanol, right? Molar volume of ethanol increases, and as the partial molar volume, it goes to. So this is for the ethanol. This is corresponding. This is the V bar that I am plotting in this curve. This is the V bar that I am plotting in this curve. Okay, of ethanol, right? So this is the molar volume of ethanol. How does it change? How does it change? It changes. It drops. You see, molar volume of ethanol drops as you increase the amount of water. Molar volume of ethanol drops as you increase the amount of water. And it goes to somewhere like between 14 and 16, something like 15. But if you look at molar volume of water, as you increase the ethanol content, it goes from pure water and then it decreases, and it decreases up to 14. It goes to like 14. As you have like nearly 100% ethanol, right? Obviously, it is not fully 100% ethanol, then water is not there. But water is there, it's a very high volume of ethanol, and water is very, very small. It's like a dilute solution, okay? So, I will talk about dilute solution, I will talk about Raoult's law and all. So, but you have to understand the concept. The concept is this: partial molar volume is the molar volume concentration or molar volume, the change, the contribution of water to the change in the overall volume of the mixture of ethanol and water. So, you have a mixture of ethanol. So, please try to understand the concept here. You have a mixture of ethanol and water plus water solution. You can call it water solution. Now, in this solution, what is the contribution of water? Okay, if water is the solute and say ethanol is the solvent, that means ethanol is in much larger proportion. Now, what is the partial contribution of water to the overall volume of the mixture. This is what is basically defined as the partial molar quantity or partial molar volume. So that means if you have a mixture where you have N1 moles of component 1, say N1 moles of ethanol, N2 moles of water, and you have some NC moles of some ink and so on. So you have all of these and you are mixing it. Now if you want to find, say, the partial molar volume of component I, okay, partial molar volume. Note the very important term here, distinction here. You are looking at partial molar volume of component I. You want to see the overall volume of this mixture, how the overall volume changes as a function of change in the mole number of I, keeping temperature, pressure, and mole number of all other components fixed. If you see the partial molar volume is this Vi bar, then is termed as the partial molar volume of component I or contribution of component I to the total volume in the mixture. Okay, so the partial molar volume is the contribution of one of the components to the total volume of the mixture. Okay, so if you have a mixture of two components, for example, you can write and say you are taking fixed temperature and pressure, then you can write an exact, because volume is an exact differential, right? Volume is an exact differential. It's a function of temperature, pressure, mole number of A and B. So it's a binary mixture of A and B. So mole number of A is Na and mole number of B is Nb. Then dV equals to del V del Na, where P and T are fixed. Again, P and T I have kept as fixed. Okay, so that's why I did not care about writing that term with dP and term with dt, because dt and dP are equal to 0, right, at fixed pressure and temperature. Now you have del V del Na PTNB into DNA, right? Plus del V del NB and differential of NB, and you have here P, T and Na constant. Note that here Na is constant, Na does not change, here NB does not change. Here I am looking at the change in volume, overall volume, due to change in mole number of A, keeping pressure, temperature and NB constant. In the other way, it is like change in volume due to change in mole number of B, keeping pressure, temperature and Na constant. Now this you can express as V bar DNA plus V bar B DNB. Now think of Euler equation. Euler equation tells you V is nothing but V bar Na, because you have done this Euler equation. So it's analogous to Euler equation. See, ultimately, if you integrate this, for example, the amount of Na and Nb are fixed, say. If the amount of Na and Nb are fixed, so you are going from, say, if you want to integrate, it goes from 0 to Na, and this goes from 0 to Nb. But overall Na and Nb are fixed, so at amount of Na, if I add more Na, I have to take out more some Nb, right? So basically, if that is so, then basically you can write that V equals to nothing but V bar ANA plus V bar BNB. Okay, this is exactly analogous to Euler equation, which we wrote as U equals to PV minus TS plus mu I Ni. So if you do that, then dV equals to V bar A dNA plus V bar B dNB plus Na dVA bar. See, there is a Na and the differential of the molar volume of A, and there is a differential of the molar volume of B. Now compare 3 and 1. Compare this equation to 1. Now if you do that, you see VA bar and VB, see Na dVA bar, right? Change in the differential of the molar volume of component A and differential of the molar volume of component B. So differential of molar volume of component A is weighted with the mole number of A, and this is weighted with the mole number of B. What you are getting, Na dVA bar plus NB dVA bar equal to 0, right? So that's the idea. So in general, if Z is a total, Z or Z represents total property of a mixture, Zi bar or Zi bar is the partial molar property of component I in the mixture. Partial molar component property of component I in the mixture is given by Zi bar. Okay, you have N1 moles of component 1, N2 moles of component 2, Nc moles of component C in the mixture. Okay, so, and as you know, this Z, you can identify Z with G also. Say for example, Euler equation for G or Gibbs free energy is H minus Ts plus mu1 N1. See, this I have all defined, and derived, right? So it becomes this, right? Which is H minus Ts is nothing plus U plus BV minus Ts, mu1 N1, mu2 N2 up to mu j Nj, right? You have say J components. Now, as you know, if I do dg is du plus pdv minus tds plus VDP, right? PDV plus VDP, and this is minus SDT. Then mu1 dN1, mu2 dN2, N1 d mu1, N2 d mu2, right? Now, if you think of that, you have du, since du is TDS minus PDV according to first law, so du, PDV and TDS cancel. So you have VDP minus SDT and all these terms, right? Now, what I am telling is this is VGP minus SDT plus all these terms, right? So this is your equation 1. But we also know G is a function of temperature, pressure and mole number, and we can write an exact differential, which is del G del PT Ni, which is basically V, del G del T is minus S, dt, Pni constant, and there is this summation, right? We are writing this entire thing as summation, del G del Ni dNi, right? Del G del Ni dNi. Remember, del G del Ni dNi. This is a alternate way. This is the exact differential, right? It is the exact differential. And it's a function of temperature, pressure and mole number of different components I, right? I varies from 1 to C, say. So it's an exact differential way, and this is coming from the Euler equation. If you now compare 1 and 2, you get what is called a Gibbs-Duhem relation. Remember, for all partial molar property, whether it is partial molar volume, whether it is partial molar enthalpy, partial molar entropy, partial molar Gibbs free energy, or partial molar Gibbs free energy is basically nothing but chemical potential. Right? So you have already seen this, that Gibbs-Duhem relation basically gives you Na, N1 d mu1 plus N2 d mu2 plus Ni d mu I equal to 0. And mu I is del G del Ni Tp in J not equal to I, right? J not equal to I, because we are changing mole number of I. We are not changing mole number of any other component, which is the partial molar Gibbs free energy, or more commonly known as chemical potential of component I in the mixture or the solution. So in the next, in the subsequent lecture, the last lecture, I will continue with this, and I will show how differently, say for example, mu I can be written as del u del ni, as you remember that all of these are related by Legendre transform, and you basically replace one by the other. So for example, del u del ni, you are taking S, V and Nj constant. In del H del ni, you are taking S, and instead of V, you are taking the conjugate, right, which is P, right, S, P and Nj constant. Del F del ni, which is basically the Helmholtz free energy, you are taking V. Instead of S, you are replacing it with T, and P you are replacing with V, right? So physically, if you think of this, S and V and N, so here you have taken V's there, but T, right? Instead of S, you are taking T, right? So basically, S, and as you remember, T comma S are have conjugate relation, P comma V have conjugate relation, mu comma N have conjugate relation, right? So basically, if I am looking at mu, so I don't care about this conjugate relation, but see, ultimately, if I, instead of S and V, I replace it by P and T, right? S and V I replace by P and T, I basically get the chemical potential in terms of Gibbs free energy. So this is a change in Gibbs free energy, total Gibbs free energy. Remember, G here is an extensive quantity, it's not Gm. G is an extensive quantity. The change in total Gibbs free energy as a function of, due to change in mole number of component I, keeping all other components mole number constant and pressure and temperature constant. Okay, so this is how we will continue in the next lecture. We will continue and see that what are the consequences of this and how to model this, and how to create these different models of solution, right? Quasi-chemical models. I'll come to that. Okay, so in the following lectures, in some of the following lectures. Again, if you have any problem in understanding the concepts, you please drop a line in the forum, and also I am trying to arrange to give you all the solutions up to week 8. After once week 8 is completed, I will give you all the solutions, or consolidated solutions from week 0 to week 8 assignments. So in fact, I am planning to conduct a live session after week 8. I will let you know once everything is finalized. Thank you.